A-level specification, Mathematics A for OCR. So today we're going to be doing C and D. Yesterday we did A and B, and we're just going to carry on where we left. So 1.01c says be able to show disproof by counterexample. And also says at the bottom, learners should understand that this means given a statement, Px is true, then Qx is true, find a single argument which falsifies it. As an extension to this and the next point, we also need to know what an integer is, a real number, a rational number, and an irrational number is. It's going to be really useful for disproving and proving a lot of statements, as they're often involved. Last but not least, we're going to be going through some proofs by contradiction. Now, we'll go through the two that they have listed in the specification. I don't think it'll get much harder than that. We could go through harder proofs once we do the rest of the specification, but for now we'll stick with the two that they have given us. The best way to do a proof, well, do a disproof by counterexample is just choose a number by random. So let's say we have a statement like this. If n squared is a square of an odd number, then n squared plus n is also odd. And the question will ask you something like prove this statement or disprove by counterexample. So we're just going to choose a number by random, because chances are, if it's wrong, then it's badly wrong, and we can choose anything. You can have an educated guess, of course. So we're going to choose n equals 3. Then n squared plus n will be 3 squared plus 3, which equals 9 plus 3, which equals 12. 12 is even, so we're done. Another example here is for any n squared plus n cubed is odd. I'll leave that as an exercise for you to do. If you get stuck, just look at the answer that I've got down. Next, we're going to be looking at the integers, the real numbers, the rationals, and the irrational numbers. Now, we'll start off with integers. Integers are basically just whole numbers going from minus infinity to infinity. And the list of all whole numbers from minus infinity to infinity are called the integers. A rational number adds on to that a little bit. So for example, you can't have 3 over 2. That's not a whole number. You can't have that as an integer. Rationals take care of this, where you have a over b, where a and b are both integers. E just means that a and b are part of the set on the right. Yeah, a and b are both integers, and you can now include fractions as well on this list. So to be a rational number, you can just be an integer, but you can also have the additional quality where you have 9 over 4. That'll be a rational number which is not an integer. Minus 2/3, and all the way up to infinity and minus infinity again. Irrational numbers. Now, irrational numbers are numbers which cannot be expressed as rational numbers. For example, you have root 2 right here. Root 2, there's no fraction in the rationals which can express root 2 as a number. So the irrationals take care of this. So some examples of irrational numbers are minus root 2, minus root 2 over 2, root 2, root 5, all the way up to infinity and minus infinity. Last but not least, we have the real numbers. Now, the real numbers take care of everything that the irrational numbers don't. For example, you have minus c. You can slap down the calculator and see what you get. You have pi. You also have square root 5. Now, the point I'm trying to make here is root 5 is an irrational number, which is also real. And you can also have something like 11 over 2. Just before 6, which is a rational number, as well as all the integers, minus 2, minus 1, 0, 1, 2, 3, 4, 5, 6 numbers. We'll look at complex numbers later, don't mind that right now. This is just a useful image to get through your head, that you're not mutually exclusive to any one of these. If you're an integer, you're also a rational number, you're also irrational, you're also a real number. If you're rational, you can be irrational, and you're a real number too. And if you're irrational, you're also technically a real number. However, if you're a real number, you're not. You can be in one of these three groups. However, there are also numbers here, for example, pi, e, 2e, 3 pi, which are mutually exclusive to the reals and the complexes. Here you can have root 5. A rational number will be 3 over 2. And we'll just have 1 here. Now, here you can see a little bit clearer how you can be in one of them, but not in another. Hopefully this image has helped a bit in making you understand. Last but not least, we're going to be looking at proofs by contradiction. To do a proof by contradiction of a statement, you assume it's false and you come to a contradiction. Once a contradiction has been reached, you can deduce that the original statement is correct, and then you'll be finished. Now, the first proof by contradiction we're going to go over is this one here. Root 2 is an irrational number. Like we said before, to do a proof by contradiction, you assume the statement is false, and then reach a contradiction. So we're going to assume that it is rational. A rational number is of the form a over b, where a and b are integers and b doesn't equal 0. So I've decided to square both sides. When you square root 2, you obviously get 2. When you square a over b, if you look at the next line, you'll get a squared over b squared. I'll just work out here so that's not confusing. Now, I've multiplied both sides by b squared, and you get 2b squared equals a squared. We know b doesn't equal 0. We also know that there is no square number that fits this statement to satisfy a. Because we know that the squares, this part here you don't actually have to do in the exam, but I've just tried to, show something to make you visualize how it works. There's no square number which is double of another square number. The gap just gets increasingly bigger, so from 0 to 1 the difference is 1. Then it's 3, then it's 5, then it's 7, 9, 11, 13, and so on. The gap between the numbers will never satisfy the equation 2b squared equals a squared. The only case in which the above statement could be true, now you'll start writing this. It's just a little interval. You'll start writing again here, so to satisfy a, and then you'll start writing here. The only case in which the above statement could be true is if a equals b equals 0. But we know b doesn't equal 0, so a contradiction has been reached and we're done. Then I've just put a little square here to show that the proof is done. The next proof we're going to be looking at is this one right here. There's an infinite number of primes. So again, proof by contradiction, we assume that the statement's opposite is true, and then reach a contradiction. We let big N, we're assuming that there are finitely many primes, and we've called these primes P1 to Pn. We let N be the sum of all these primes plus 1. Now if we divide N by any existing prime Pk, we will always get a remainder of 1. I hope you can see how that is true. And we can repeat this for any prime pk in our list. However, every integer greater than 1 is divisible by at least one prime. But none of the primes in our finite list divide n. So it follows that n is divisible by a prime not in our list. So we've reached a contradiction. And that's the proof finished. So we finished the whole of section 1. Let's recap. So, today we did part C and part B, and we were able to disprove by a counterexample. We know what integers, rational numbers are, irrational numbers, and we also know what real numbers are now as well. We also did part D. We were able to understand and be able to use proof by contradiction. In particular, we did also learn how to do those two proofs named in the list.
If you liked today's video, like and subscribe. If you got any comments for me for which I can improve on, or what you want me to do next, just leave them in the comment section below. I always try to read through all the comments. Thank you for watching.